Today, we're going to be building doctors, and our patient? It's concrete. You know, it's the silent, super strong foundation of our entire world. But guess what? Even the strongest materials can get sick. So let's scrub in and start the examination.
I mean, just look around you for a second. The bridges you drive over, the buildings you work in, the sidewalks, it all depends on this man-made rock. But here's the catch we almost always forget. Concrete gets old, it gets damaged, and it falls apart. And understanding its weaknesses, well, that's absolutely crucial for keeping our world safe and standing.
So, if we're thinking of a concrete structure as our patient, how do we know it's not feeling well? Well, just like any good doctor, we're going to start by looking for the obvious signs, the symptoms on the surface that are telling us something much deeper might be wrong.
Cracking. This is by far the most common symptom you'll see. Think of it like the patient has a fever. It's a huge, flashing signal that something is up, but it doesn't tell you what's causing it. It could be nothing, a minor cold like a little surface shrinkage, or it could be a sign of a much more serious disease.
Now, if cracking is a fever, spalling is, well, it's more like a deep, open wound. This is when chunks of concrete literally pop right off, and you can see the steel skeleton, the rebar, hiding inside. This is usually caused by some massive pressure building up from within the concrete. And let me tell you, that is a very bad sign.
You ever see a sidewalk or a patio that looks like its top layer is just peeling off? That's what we call scaling. It's basically the concrete version of a really bad sunburn. This is almost always an environmental problem, caused by stuff like freeze-thaw cycles that just attack the surface, layer by painful layer.
And then you've got this stuff, honeycombing. This one's kind of like a birth defect. It's not something that happens over time, it's a flaw that was baked in from day one. It happens when the concrete mix wasn't placed right during construction, leaving these little voids. And those voids, they can become major weak points down the road.
Okay, so we've got a patient with a fever, some pretty nasty wounds, maybe even a pre-existing condition from birth. But hey, a good doctor never just treats the symptoms, right? You have to find the root cause. So the big question is, what's the actual disease making our concrete so sick?
All right, so for Act 2, we're shifting gears from just looking at the problem to actually investigating it. It's time to put on our diagnostic hats and figure out what is really causing all these issues. Now, all the things that can go wrong with concrete might seem kind of overwhelming, but you can pretty much boil it all down to three main culprits. First, you've got attacks from the environment, things that cause scaling. Second, physical stresses, from the weight and loads the structure has to carry. And third, those construction flaws we just saw with honeycombing, problems that were there from the very beginning. Okay, now check this out, because this is where it gets really interesting. This slide shows how physical stress works, and it's not always obvious. You've got the same force, just a simple downward load, but it creates tension in totally different places depending on the design. On a simple beam, held up on both ends, the tension pulls at the bottom, so that's where cracks start. But on a balcony, what we call a cantilever beam, the tension is at the top. So, and this is the key, where you see the crack tells you a whole story about the forces at play.
Of all the diseases that can infect concrete, corrosion is probably one of the most dangerous. It's such an insidious problem because it starts deep inside where you can't see it. Water and salt seep into the concrete, they find that steel rebar, and they cause it to rust. And here's the killer part. Rust takes up way more space than the original steel, creating this insane internal pressure that literally blows the concrete apart from the inside out. That spalling we saw earlier, yeah, this is often the villain behind it.
So, we know the symptoms. We know the possible diseases. But you can't just cut open a bridge to see if its steel skeleton is rusting away, right? So how in the world do engineers, our building doctors, do a proper checkup? How do they see what's happening inside without resorting to major destructive surgery?
And that leads us right into our final act, the examination. Let's take a peek inside the modern engineer's toolkit. And I'm telling you, it is filled with some incredibly clever, high-tech gadgets for figuring out the health of a structure, from its skin all the way down to its core. So the checkup usually happens in 3 stages. You start with the simple stuff, a visual inspection, just using your eyes to look for all those symptoms we talked about. If you need to know more, you might move to what's called semi-destructive testing, which is kind of like taking a tiny biopsy, maybe drilling out a small core sample. But the really amazing stuff, that's the third tier, non-destructive testing, or NDT. This is basically like giving the building an MRI or an X-ray. And this table here shows just a few of those advanced scanners. You've got something simple like a rebound hammer that just tests surface hardness. But for a deeper look, you can use ultrasonic pulse velocity,
where you're sending sound waves right through the concrete. If the waves travel fast, the concrete is solid. If they slow down, it means you've probably got internal cracks. And to hunt down that hidden killer, corrosion, they can use electrical tests like half-cell potential, which can actually predict the chances of rebar rusting inside.
So, let's say an engineer runs one of those electrical tests, a half-cell potential test, on a big bridge column. They place their little probe on the surface, and the meter gives them a reading. The number comes back minus 400 millivolts. So, what does that even mean?
It means this. The industry standard tells us that any reading more negative than minus 350 means there is a greater than 90% chance that the steel inside that column is actively rusting away at that very moment. Just like that, an abstract number becomes a crystal clear and very, very serious diagnosis. Suddenly, the invisible becomes visible.
So what's the big takeaway here? It's that diagnosing a sick building is an incredibly sophisticated process. It all starts with something simple you can see, like a crack, but it can lead all the way to measuring invisible electrical fields to understand a chemical reaction happening deep inside. It's really this powerful combination of old-school observation and cutting-edge technology. And that leaves us with one last question. For you, the next time you're driving over a bridge or walking through a parking garage, don't just see a boring old slab of gray rock. Look a little closer. See if you can spot the symptoms. Because now you know that a simple crack isn't just a crack, it's a clue. It's part of a story. So what story is the concrete around you trying to tell?